Here's a question that sounds like it belongs in a supervillain's lair. Could you air condition an entire country? Not just the buildings, the whole thing. Open sky, farmland, cities, everything. The technology exists, the math is doable. So let's take this completely seriously, run the actual thermodynamics, and find out exactly where it stops being engineering and starts being a climate catastrophe. The answer is sooner than you think. But let's be specific.
First, let's pick a country. The United States is the obvious candidate. It already spends more energy on air conditioning than the entire continent of Africa uses for everything. But for this exercise, let's use something more tractable. Let's use Singapore, a city-state of about 730 square kilometers, sitting almost exactly on the equator, where the average temperature is 31 degrees Celsius, and the humidity makes it feel significantly worse. Singapore is small enough to calculate, hot enough to matter, and already obsessed enough with air conditioning to make the question feel almost reasonable. The first number we need is the heat load. How much thermal energy does Singapore need to shed to drop its outdoor temperature by, say, 10 degrees Celsius, from 31 to a comfortable 21? Air has a specific heat capacity of about 1,005 joules per kilogram per degree Celsius. Singapore's atmosphere, the column of air above its 730 square kilometers, up to a meaningful height of about 2 kilometers, has a mass of roughly 1.8 trillion kilograms. To cool that mass by 10 degrees requires 18 quadrillion joules of energy removal. That's 18 petajoules. Singapore's entire annual energy consumption is about 900 petajoules, so cooling its outdoor air by 10 degrees requires energy removal equivalent to about 2% of its annual consumption. That's surprisingly manageable. The engineering problem seems almost solved. And then we hit the second law of thermodynamics.
Air conditioning doesn't destroy heat, it moves it. Every air conditioner takes heat from one place and dumps it somewhere else. That's the whole mechanism. Your window unit cools your room by heating the air outside your window. This works fine at room scale because the outside is enormous and absorbs the heat without noticeably warming up. At country scale, the outside is the problem because the outside is also inside. To cool Singapore's outdoor air, you need to dump 18 petajoules of heat somewhere. But there is no outside. You're cooling the entire country. Every joule of heat you remove from the air has to go somewhere beyond the borders, into the ocean, into the upper atmosphere, or into neighboring countries which will have opinions about this. Let's say we pump it into the ocean. The waters around Singapore, the Strait of Malacca and the Singapore Strait, have a combined volume of roughly 20,000 cubic kilometers. Water has a higher specific heat than air, so dumping 18 petajoules into this volume raises its temperature by about 0.2 degrees Celsius. That's manageable. For one day of cooling, Singapore's climate is year-round. Running this system continuously dumps roughly 6,500 petajoules into the surrounding ocean annually. The local ocean temperature rises by several degrees within a few years. Warmer ocean means more evaporation. More evaporation means more humidity over Singapore. More humidity means the air feels hotter. The air conditioners work harder. The ocean gets warmer. The cycle accelerates. We have air-conditioned Singapore into a feedback loop.
Let's scale up to the original question and try a larger country. The continental United States covers about 8 million square kilometers, roughly 11,000 times the area of Singapore. The heat load scales accordingly. We're now talking about removing energy on the order of 200,000 petajoules to achieve meaningful outdoor cooling. The U.S. generates about 25,000 petajoules in energy annually from all sources combined. Cooling the outdoor air requires 8 times the country's entire energy supply, just for the thermodynamics before we build a single unit. The waste heat problem is now continental. You cannot dump continental-scale waste heat into the ocean without measurably warming it. Warmer oceans mean stronger hurricanes, disrupted weather patterns, and in a deeply ironic turn, higher average temperatures in the interior of the continent you just tried to cool. The air conditioning makes the country hotter.
There is one partial solution: cool only the inhabited areas, not the entire landmass. The U.S. population is concentrated in about 3% of its total area. Cooling just that 3% brings the energy requirement down to something approaching the merely absurd rather than the physically impossible. You'd still need to solve the waste heat problem, you'd still need a power grid capable of running the equivalent of several times the current US generating capacity, and you'd still need to explain to farmers why their crops are growing in an outdoor sauna while city residents enjoy a permanent 21 degrees. The air conditioning itself is fine, by the way. Window units, central systems, industrial chillers, all mature technology. We've completely mastered making small spaces cold. The thermodynamics is the part that keeps getting in the way.